Okay, let's move on to the next one, which is conceptually, at least for me, a bit more challenging. At least how to reduce it, how to beat it down to an instance of GTV minimization. And this is called vertical federated learning. In vertical federated learning, all local data sets consider, or one special case of vertical federated learning, all local data sets have data about the same data points. Consider, for example, all people who have a Finnish social security number, including me. And all those people have information that is stored at different locations. For example, there is my bank, my home bank, has information about me which is not available to the, I hope, not too much available to the tax office. Then there is another bunch of properties of me that is available to the Kela or to my healthcare provider, Terveystalo, which I hope is not fully available to my employer, which is Aalto University. So you see, each one of us contributes or makes a contribution to different data silos. And yeah, another example, very important example is like loyalty cards. So for example, if I would have this escortee, which I'm regularly asked for, but I still resisted, then there would be S-Market. The company behind S-Markets would be another local data set. So all the nodes here are now these different institutions or organizations or companies in Finland that all have different kinds of information or properties about the Finnish population. And then there's this, I mean, maybe you have heard this of how's it called? Cross-referencing information. So this is vertical federated learning. How can we train a model by exploiting all this information without privacy leakage? So how can we train an optimal shopping advisor for S-Market or Lidl or any other K-Market or Aleppa? Now I have to name all retailers. How can we develop such an app by using information from Kela, using information from tax officials, and so on and so forth, without breaking privacy laws? Or in the other direction, for example, the government wants to cut down healthcare costs. So the best way would be, as I understood, one good way to save healthcare costs is to motivate the population to eat healthy. So how to leverage all these different data silos to develop a government-based shopping advisor or shopping recommender. Yeah, so this is vertical federated learning. All local data sets have the same, contain the same data points, but they use different features. And maybe even the labels might be available only to one of these nodes. So only one of these nodes knows the labels, like the health status of the population. Okay, but I have shown here, I have worked out a bit the reduction of vertical federated learning also to another special case of GTV minimization. And I was only able to do this somewhat nicely if I assume that all devices or all nodes, or in this case, all kinds of retail shops, Kela, they all also have access to the labels. So the label is known to all the participants in the federated learning network. And this might be a restrictive assumption, but I needed it for my argument. That's why I made it. And for some applications, it might be actually not too unreasonable to assume that all nodes which have data about the same population, they know something about the population. They have common knowledge about the population. And this means that they all know the labels. And if you work out then this example here of linear regression, it turns out you can write this linear regression problem as a form of consensus problem. So you want to learn, I have introduced here this auxiliary model parameters S, and this model parameters S should be a copy of the of the predictions delivered by the global linear model. So you train underlying, you want to train a global linear model, but you want to train it in a distributed fashion. So how do I do it? Well, I say I copy this global linear model using this artificial or auxiliary model parameters SI. And to ensure that these auxiliary model parameters are all the same, I put them at the nodes of a well-connected federated learning network and make alpha large enough. So if I choose alpha large and have a connected network, then when I minimize this GTV minimization problem, as we have shown already or discussed in previous lectures, the result will be that these auxiliary variables S superscript I, one auxiliary model parameter for each node, they will become the average of all the network, the parameters at the network nodes, and this average is exactly the prediction delivered by the global linear model. So I have walked down these steps in somewhat detail in the slides, which I very much welcome you to try to follow yourself. Yeah, so the basic idea is to write this linear regression problem as a distributed or a consensus problem. So instead of having one single model parameter, S, that is actually this S here are the predicted labels, the predictions that we get from a linear model. We copy this S for each node in the network. But then we force these copies to agree, to be in consensus. And this is a nice trick which is not invented by me. This has been studied also for decades in distributed convex optimization. When you want to solve an optimization problem that involves information distributed over a network, when you want to solve this in a distributed fashion, formulate a hypothetical centralized problem and then copy it or clone this centralized problem to all nodes and force them to agree. So this is a very versatile design pattern for distributed optimization methods. And if you apply this trick or this design pattern here, it turns out you can write vertical federated learning, tada, as an instance of GTV minimization. However, I must emphasize that this GTV minimization trick works only if each node in the network has access to the labels, because I need the labels here to formulate the local loss function for GTV minimization. If node I doesn't have access to the labels, node I cannot cannot implement this loss function, and my whole construction is useless. So at least when you have the same, when each node in vertical federated learning has access to the labels, you can you can train a linear model in a distributed fashion by solving a GTV minimization problem. Okay, there was a question, I think, which I will try to catch now.